Welcome to solverfy.
Hello. So, if we translate this problem into an equation, basically what you're asked to show is that there are no positive integers um, such that x to the cube plus y cubed is equal to z cubed, and with z cubed is smaller than 1000, and x and y both strictly positive. So the easiest way to answer this is to do this by do a proof by exhaustion, and that means checking all the different possible cases. But notice that there are quite a lot of different possibilities. In fact, there are 729 possibilities if x, y, and z are chosen independently, and that's quite a lot. So you want to do it in a smart way so that you don't have to check too many possibilities. All right, so the first thing to do is to note down all the different cubic values under 1000. And so you start off with 1. 1 to the cube is 1, and then 2 cubed is 8, 3 cubed 27, 4 cubed 64, 5 cubed 125, 6 cubed is 216, 7 cubed is 343, 8 cubed is 512, and 9 cubed is 729. Okay, now one way of reducing the number of possibilities is to see that x and y must be smaller than z. Okay, the reason being is that x and y cubed are both strictly greater than 0, and therefore if we have numbers xy plus y cubed equal to z cubed, then you necessarily need x cubed to be smaller than z cubed, and since the polynomial x cubed is increasing, that implies that x is strictly smaller than z, and the same argument holds for y. So that, for instance, already means that you don't have to check, for instance, x equals 4, y is 5, and z 2, right? Which makes sense. Okay, so the way to approach this is to say, all right, let z be equal to 1 or 2 or 3, and show that at each step you will not have any combinations of x and y which satisfy this equation. So you already know that z cannot be equal to 1 because x and y are strictly smaller than z, all right? And there is no strictly positive integer smaller than 1. So you start with 2, okay? And that's quite easy because then there's only one possibility, x and y can only take the value 1, and you can see that 1 cubed plus 1 cubed is, so it's equal to 2, which is different from 8, 2 cubed. So z cannot take the value 2. So, if you are to write this down very, very rigorously, you should say, so suppose, for the sake of contradiction, that there are these integers, and you start off by saying, okay, so say z is equal to 2, and then you continue the argument and show that this cannot be possible. And then you continue on with all the different possible values of z. Okay, now if you take z is equal to 3, then z cubed is 27. And now there are different possibilities. There are 3. The first one is x is equal to 1 and y is equal to 2. And the second one is x equal 1 and actually, okay, so that's like that. If you do it methodically, that's the first one. And then the other one is x and y both equal to 2. You could argue that x equal to 2 and y equals 1 is a different option, but it's basically the same as this one, all right? And well, you can see that in both cases, x cubed plus y cubed is equal to 1 plus 8. 9, all right, which is not equal to 27. In this case, we've already seen it. That gives you 2, which is not equal to 27. And here, 2 to the 2 cubed plus 2 cubed gives you 8 plus 8, 16, which is different from 27. All right. Now, in addition, you should note that 16, 2, and 9, which are the consequences of choosing x equals 1, y equals 2, and etc., are not part of this table here. Okay? So we found here 9, 2, and 16. 9, 2, and 16 are not part of this table of value, of this list of values. And so we don't have to check those combinations anymore because we've shown that these two combinations don't give a perfect cube. All right, and that actually makes it quite easy for z equals 4. So we say z equals 4, so z cubed is equal to 64. And now the only values we have to check are actually x equal to 1, y equal to 3, x equal to 2, y equal to 3, and x equal to 3, y equal to 3. The reason being that you can see that if we have one number being equal to 3, then we have here all the different options. Now, if y is equal to 2 and x a number smaller than 3, then we enter this scenario here, and we've checked that these numbers don't give a perfect cube. So you only have to check these three numbers, these three cases, and I mean that's quite easy to check. 1 cubed plus 3 cubed is 1 plus 27, 28, which is different from 264. 2 cubed plus 3 cubed is 8 plus 27, which is 35. And then finally, 3 cubed plus 3 cubed is 27 plus 27, that's 54, which is not equal to 64. So again, we've shown that z cannot be equal to 4 if we are assuming that there is a solution, right? And in addition, note that for all these combinations, so 28, 35, and 54, we haven't reached any of the numbers on this list. All right? And basically, all you have to do is to continue this reasoning. And I'll just do it again for z equals to 5. So if z equals 5, then z cubed is 125. And so here, again, we only have to check a few options, namely 4, which is x equals 1 and y equals 4, x equals 2 and y equals 4, x equals 3, y equals 4, and x equals 4 and y equals 4. So again, why are these 4 options the only options we have to check? Well, basically, you first of all have to dismiss all options where x and y, where one of x and y is equal to 5 or is 5 or greater. Okay, so that leaves us with x and y taking the values between 1 and 4. Since this situation is symmetrical, if we consider x equals 3 and y equals 4, that's the same as considering x equals 4 and y equals 3. And finally, all the previous cases, such as, let's say, x equals 2 and y equals 3, have already been checked previously in this case here. Okay, so these are only the 4 options you have to check if z takes the value 5. And okay, that's mechanical. Y 1 cubed plus 4 cubed is 1 plus 64, which is equal to 65, different from 125. 2 cubed plus 4 cubed is 8 plus 64, which is 72. different to 125. 3 cubed plus 4 cubed is 27 plus 64, which is equal to 91. And then 4 cubed plus 4 cubed is 64 plus 64, which is 128. And all these values are different from 125. And in addition, you can see that these four values here, these four values are different to any of the values in this list. Okay, and so basically you simply have to check for z is equal to 6, 7, 8, and 9. And by exhaustion, you will have found that this equation here has no values for which z cubed is smaller than 1000, and it has no positive integers which satisfy this equation. And it is in fact a more general there's a more general theorem, a very famous one called Fermat's last theorem, which shows that for n greater or equal than 3, there are no solutions to this equation here. No positive integer solutions to this equation, which is a theorem which took about 400 years to be solved, and which was solved 20 years ago by Andrew Wiles. Okay, and this here is a specific case of this larger theorem. All right. Now, this proof by exhaustion is quite interesting, and it's quite important, especially if you are trying to implement a program. Let's say to implement this in a program, it's always important to try to reduce the number of combinations to check by using very simple logic. For instance, here to say that x and y are strictly smaller than z, reduce considerably the number of steps of combinations to check. All right. Hope this helped, and have a good day.